Hello and welcome. So in this video, we will implement Redis with the help of Python. The goal of this video is to let you understand the advanced concept of Python. For example, Python concurrency, async, await, event loop, how to implement socket in Python, TCP, UDP. But if we go if I tell you what's the TCP, how HTTP2 differ from HTTP3, this becomes quite boring. So why not to implement these things when we implement the Redis and learn a lot of things that we don't know, because we actually just take the advantage of working on the frameworks, for example Django, Flask, Fast API, without knowing that much about how the things works under the hood. So in this video we will learn how Redis accepts multiple connections on a single thread by the help of IO multiplexing. We will implement it as well, and also we will see how Django do when we say Python manage.py run server. Basically Django only runs one process and handles every connection on that only. So these type of things we will learn, and it will be like a long video, and I have divided this in mainly 8 parts, and I will make sure that it don't become that boring by going through the Python coding examples, and a lot of practical implementation will be there in this video. The code can be found on the GitHub repo shared below, part by part. So let's start. So these are the main segments on which this whole video is divided. So first we will start with implementing concurrency. So first we will learn what is concurrency, what is GIL in Python, what's the benefit, what's the disadvantage of it, what's multiprocessing, parallelism, multitasking, and multi-threading, these basic things. Then we will go on to implementing event loop with the help of Async IO package, and how we can use event loop to make so blocking socket to non-blocking sockets. So basically we'll learn about the sockets as well in the part 3. Then we'll go in the part 4 about understanding the TCP and UDP protocols, how the three-way handshake sync happens, and then we'll understand how UDP, because you don't have any data flow ordering, how it is faster, these type of things. And then we'll go with the HTTP, understanding the HTTP basics, using the selectors module and module. And this selector module is actually used when we see the Django code, and we'll see it by opening the Django repo, how by the help of socket server.py and the run server.py file, Django is actually handling the multiple connections and simultaneously. Then we'll start with the Redis implementation, but once we have our core build up, and even we will start implementing few of the things in the parallel in previous part also, but we will summarize the things in part 7, and we will learn how we can further optimize the Redis that we have implemented for the real life cases. So the goal of this video is not just to basically implement Redis or anything, but to tell you about the concepts, but to explain the basic fundamental concepts of backend engineering. So I hope you will like this video. Okay, so first let's start by looking at basic terminology, like what is concurrency, what is parallelism, what is GIL. So at this time we are looking from the perspective of Python, but also from the perspective of basic computing and basic networking into the mind. Okay, so concurrency means when we are executing multiple tasks simultaneously, maybe not parallelly, right? For example, so as you can see here, that we have this particular task running, then we run this then we run this task, then we run this task. So you can see, then we run this task actually. So you can see at one time only one task is running, and then we are kind of switching across the task. So this task will run after little time here, then here. So at one time we are running particular one task. So this is kind of concurrency, right? But not parallelism. Okay, we are not running 2 or 3 tasks in parallel, but as you can see here, this is concurrent but parallel. Okay, it is also parallel, all the 3 tasks are running simultaneously. So a more common example that is often given person, let's say this is like dominoes order taking person, and if there are two queues, so first he takes the order from this, then he takes from this. So at one time he's taking one order but doing the work concurrently. But here the two things are there, two person are there, and they are parallelly taking both the queues. So this is parallelism. Okay, this is your parallelism. But here this is concurrency. Why concurrency? Because let's say when this person gave the order to this person, then this person's order was taken, and this was kind of like maybe the order printing was done, or maybe the food was getting prepared. So these type of things were happening in the background. The time when order was taken from the second person, the first person other tasks were being processed in the background that this person was not doing. Correct? So he can take the task of second person without getting blocked. This is very important, that the counter person, the person sitting on the table, can take the order of the second person, because first person's work is not done by him. Let's assume like pizza is getting prepared, so he can take the second person's order, right? Instead of getting blocked, okay, I will only take the second person order once you are free, the first person is free, so he can't say so. Correct? So this is this is what we call concurrency. Okay, so concurrency means like we are executing the multiple tasks but not in parallel. So this task is good when we have IO bound tasks. Okay, so this concurrency is good when we have IO bound tasks. So for example, let's say you have an application and your application made a query to the database. Okay, and this is your DB. Your application made a query to the database will give the return the response back. So in this time, because your application is waiting when it made a call to the database for the response, this is like if waiting period is there. So the application can perform some other work when it was waiting for the reply from the database. This is where the concurrency, the power of concurrency comes into the picture. Okay, and we will see like how to implement this in Python. Okay, so first thing to understand is like there are two things. One is IO bound task and one is CPU bound task. So IO bound tasks are like DB calls, or for example reading a file. Let's say you have a large file, then you have to read that file into the memory, okay, by let's say pandas pd read underscore csv. In that case, your code, your application can take some time. You can do something else, that is IO bound task. Other thing that is there is like, for example, the very important thing is like API call. API call is also IO bound task. Let's say you're making an API call to, let's say, Facebook Meta APIs. So you're calling meta.com / let's say some conversation APIs. So you're waiting for this response to come to your application. So this is also IO call, okay, IO bound task. So these are IO bound task. IO bound tasks are for which your application is waiting, and in the meantime it can perform other tasks, giving the power of concurrency. Then there comes CPU bound task, where you are actually doing the computation. For example, you are running an ML model, correct? In this, your core of the CPU is getting utilized. The computing power is getting used. So this is your CPU bound task. So concurrency, let's say you have only one core in the system. Now one core either can do one task, correct? It can only do the one task at one time. So if you are having an IO bound task, think about it. If you are having an IO bound task and you are having one core, so IO bound task, this is your core. If you are making an IO bound call to it, for example API call, so when till you get the reply of your API call, your one core can do something else. Can be helpful in IO bound task, but will not be useful in the CPU bound task. That's the important thing, because if this is your one core, that can perform some task, if it is already doing CPU bound task, then there is no benefit of implementing async IO, of implementing async await, because your CPU is already engaged in doing something, correct? So your like IO bound task, please use concurrency. CPU bound task, please use multiprocessing. We will come to it later. And by concurrency, like we use multi-threading. Okay, so this is important. Like if you have IO bound task, we use multi-threading. We make multiple threads. If we have CPU bound task, we have to make multiple processes. So the second thing to understand is the difference between threads and process. Okay, so let's talk about the basic difference between a thread and a process, because this is very crucial in understanding how the Python concurrency will work. Okay, so we know that when we are dealing with IO bound task, we have to go with the threading, but when we are dealing with the CPU bound task, we have to go with the process. This is the one thing. But what is this thread and a process? So we have like to understand this. So this is a program. When we execute our program, it loads, it is residing in the hard disk. When we execute it, it comes into the RAM. So the program comes from hard disk to the RAM, and it do like PCB setup, process control block setup, allocates the memory from the heap, like to the heap, to the stacks, etc. These type of things happen. And then OS do the scheduling, like when to pick up this process. Once the PCB setup and the scheduling is done, and its time comes, then OS will give the process its PID and everything. So a program in execution is known as process. So a process can have multiple threads. So this is the process that is having multiple threads now. And one thread, this is one thread. In this one thread, as you can see, the thread is having its own register, counter, stack, and data. So this thread in itself is now becoming like, this is kind of a process, but having one thread only. That is also a possibility, right? So thread is the smallest unit in execution. So thread are like kind of a basic unit that do some work, and the process can have multiple thread also. Like we have 3 thread, and you can see here the data and code of this is common across the thread, but they have their separate register, stack, and counter. These things are separate. Okay, so this is known as your this is basic thread. Okay, so this is your basic thread. So the very crucial important point here is, like when we have these multiple thread in one process, they share common address space, common memory. So they are they share common memory. So if one thread fails, because they are having same memory space, all other can also fail, right? So one thread in a process can fail other thread in the same process. But let's say we have 2 processes. This is one process P1, and this is second process P2. Now they might be having 2 thread, T1 T2 here, and here also like T1 T2. Now if T1 fails, then this process will fail, and it will not impact other process, right? It will not impact other process. So because these 2 processes are having different address memory spaces, correct? So that's the difference between a thread and a process. A thread, multiple thread inside a process shares same memory, okay, but they have different register, counter, in their own stack. That's important. Okay, but the memory is same. Now a process is independent program instance running in own memory space. Independent program instance means when we run the program, it becomes an instance, right? So program in execution is known as process. This is important. So an error in one process will not affect other process. As I told, like if we have 2 processes running, the error in one will not affect other process. Thread is lightweight. So thread is the basic unit of execution. They have same memory space. So an error in thread can crash the entire process. If this thread have some error, it can crash the entire process. So this is like one thing that we have to focus on, and this is the flow. Like this is your program. It will be first loaded from the disk to the RAM, PCB setup, and other things are also there, like scheduling and storing the address in the PCB for next execution. These type of things happen, and once like OS allows, the execution will be done of that process. Yeah, once the execution is done, it will be terminated. The process will be terminated, right? So this is the basic flow of any process. All right. So now we know what is a thread and what is a process. That's the one thing. Now let's move on to the second thing. I want to tell you like what's the benefit of having a process. So the benefit of having a process is primarily it provides stability. Why it provides stability? Because it is having its own memory space, right? So it's kind of having an isolated memory space, meaning that one process cannot directly impact other process. So it's having stability. Parallelism. Why parallelism? Because your one process may be running on one core, like P1 is running on one core of the CPU, let's say C1, and your process 2, P2, is running on another core of the CPU. So these two processes can run simultaneously if they are running on the multi-core CPU. Okay, hence parallelism are provided. Security, again, because they are more stable, they gives more security. Process, now the problem is with the speed, right? Because they are taking separate memory space, so they like they are having overhead that gives like a speed issue. Other than that, they are having like more complex implementation when it comes to the process. The communication between the two processes is done with the help of IPC, that is inter-process communication. So two processes will communicate with the help of inter-process communication. For example, there are message queues, there are shared memory that both process might be sharing, and the one of the very important thing that we will be learning, socket. So these are like few things to do the IPC like communication between the processes. So the very important thing is go with the process. I'm again repeating it, when you need CPU bound task to be done. Now we know thread is the basic unit of execution, right? So thread is good for IO bound task. If one thread is waiting, like this is your thread T1, and it is waiting for some API to return the response to be returned, so another thread can pick up some other task on the same core, giving asynchronous nature or multi-threading way. Okay, benefit. So because thread having the same memory space, we can communicate with them faster than what we do with the IPC. Okay, the communication is faster and they have same memory space, so switching between the thread is also like going from T1 to T2 and coming back from T2 to T1 is faster. Switching, this is known as context switching. This is also faster because the memory space is same. Let's assume like what happens if there are two processes, P1 and P2, and if you have to share control from P1 to P2, then the OS have to save all the state registers data, all the register data that have been like memory, there's some memory units and all of those things, okay, that they have to be saved, and then the P2 will be started. So this overhead in context switching is there in the case of multiple processes, but because thread have same address space, this overhead is not there and it have faster context switching. Communication is also faster because we don't need IPC mechanism like queue, socket, etc. to communicate between two threads. Resource sharing is also faster, right? Because obviously we are having the same memory space. So now you understand how the communication between the two thread works and how like context switching happens in thread versus when it happens in the case of process. Okay, so now understand the context switching one more time for the processes. So let's say we have P1 and P2, two processes are there. We have to give control from P1 to P2 because let's say P1 OS wants to fairly allocate the time and he want to run, like OS want to run now the P2 state. So what we have to do is we have to save the state of P1 process and we have to load whatever like let's say it was running previously, so we have to load that state also. And this time, for this time, like the CPU is not doing anything for the process P1 or P2, but doing the work for the context switching. So this is kind of a wasted time, and that's why context switching has an overhead, right? Overhead of what? Taking like saving the whatever the state of p1 is and then reloading the state of the p2. This also happen when we do reverse, for when we go from the p2 to p1. So this is like context switching, or you can say time slicing in multiple process in the case of operating system.